So what we're going to do is we're going to go through, like we did with substitution, we're going to look at the reaction type, draw the mechanism, and look at the major product. So we're going to talk about major versus minor products for some of these as well. So the first thing, just like we've done before, is we need to figure out what is the alpha carbon, where are the beta carbons, beta hydrogens, because elimination is about the beta hydrogens being removed. So the alpha carbon, you want to be careful with ones like this. The alpha carbon is where the leaving group is attached. OTS, that actually represents tosylate. So OTS represents tosylate. It's just another type of leaving group. So instead of having a halogen, tosylate is another leaving group. So this carbon, where our leaving group is attached, that's our alpha carbon. How many other carbons does this alpha carbon have connected to it? Just one. So this is a primary alpha carbon. Then our beta carbon would be here. And then any hydrogens connected to this. So we have 1, 2, 3 carbons. That means we have one hydrogen. This is a beta hydrogen. So now the first thing that we have to do is figure out the reaction type. Well, we have a primary carbon, primary alpha carbon, and let's look at what we have over and under the arrow. NaOH, how would you classify that base? Strong or weak? Strong. We know that from AP Chem. NaOH, maybe the most common strong base that we used in AP Chem, because Na plus is a spectator ion, so we have OH minus. So here's a strong base. OH minus is small. And then DMSO. Just going back, reviewing substitution reactions, DMSO is an aprotic solvent. Now let's just kind of go through and think. Could we have a primary carbocation? Is that stable? No. All right, so primary carbocation, not stable. And we have a strong base. Strong base means it could remove that beta hydrogen all at once, which is good because we're not likely to form a carbocation here. So if it's going to happen all at once, what type of reaction is it, E1 or E2? E2. Right? Happens all at once. It's a concerted reaction mechanism. So that's an E2 single step. In our mechanism, there are lots of arrows in a single step mechanism. So I'll just use a black marker to make it easy to see. I'm going to show my lone pairs. Remember, you could show the movement of arrows from the negative charge if you want as well. That's fine. But then you have to make sure you show that negative charge. A base accepts a proton. So one of the lone pairs from OH minus is going to attack that hydrogen. So OH minus is going to attack that H plus, accept it, become water. These bonding electrons, I know my arrows are crossing, but you get the idea. I should have drawn the beta hydrogen on the other side. Right, bonding electrons are going to come to this single bond to create a double bond, but we have to make sure that no carbon has violated the octet rule. So tosylate, that leaving group, is going to leave. Now if we look at the product here, right, this is all one step, so it's just lots of arrows all at once. So we have a double bond kind of sticking straight up, which is fine, right? We can have that. Were there any other possible beta hydrogens to remove? No, it was just this one. So we didn't have a choice of which beta hydrogen to remove. We only had that one beta hydrogen. And so our product, we only have one possible product. We didn't have the option of, do we have a more or less substituted? So if we look at the next one. So we look at this next one. First thing to look at, always look at your reactant. Is your reactant a primary? Is it secondary? Is it tertiary? So always look at that first. And then we also want to identify where our beta carbons, because in turn that's where our beta hydrogens are. So the alpha carbon is the one where the leaving group is connected. So here's the alpha. How many beta carbons, not hydrogens, how many beta carbons are there in this molecule? 3, right? Here's a beta carbon, here's a beta carbon, and here's a beta carbon. Beta carbons are 1 carbon out from the alpha. That's where your beta hydrogens are. So we have 3 hydrogens here, 2 hydrogens here, and 1 hydrogen here. Now, what is the degree of substitution for the alpha carbon? How many other carbons are connected to that alpha? 3. So that's a tertiary alpha carbon. Just knowing that it's a tertiary alpha carbon, is this more likely to go through steps or happen all at once? Go through steps, because tertiary alpha carbon is probably going to form a carbocation. Tertiary carbocations are the most stable carbocations that we will look at. So this is going to undergo an E1 reaction. 2 steps, carbocation intermediate. So we're going to look at the mechanism. First thing in any 2-step mechanism is that the leaving group leaves. So the leaving group leaves, form a carbocation. So because this is going to be multi-step, we have, and there's our positive. So carbocation is formed. Now for E1 reactions, we need to look at our base that we have here. All right, we have CH3OH, just to make sure. So be careful with this. CH3OH, is this ionic? No, there's no metal, right? The reason I say that is because people see the OH and immediately want to say, oh, that's a strong base. If you have OH minus with Na plus or K plus or Li plus, it's ionic, yeah, then that's a strong base. But this is methanol. Methanol is a weak base and a protic solvent. The reason that I just want to point that out is because protic solvents are good to stabilize carbocations. Now, E1 reactions. E1 reactions always form the Zaitsev product. Zaitsev product is the most substituted alkene. When we talk about most substituted, that means a double bond. So if we have 2 carbons double bonded, most substituted is tetra. If the carbons have 4 groups off of both carbons, all right, 2 off of one, 2 off the other, that's tetra substituted. That's the most substituted. This would be the most substituted. If it was just 2 carbons double bonded and these are H's, that's your least substituted. So our goal for Zaitsev product is to figure out how can we get the most substituted alkene product. So we have to look at our different options. So we have an option of removing a beta hydrogen from here, or from here. Doesn't matter which hydrogen you pick in terms of like which one of these three should you pick or which one of these two. You're looking at the positioning. So you want to see where could we put the double bond. Could we put it here? Could we put it here or here to get the most substituted product? Well, I'm going to look at the mechanism. So let's say this is hydrogen 1, 2, and 3. Which of those hydrogens could allow us to have a tetra-substituted alkene? 1. That's the beta hydrogen we're going to remove. So the only one we have to show is that hydrogen so we can look at the removal. So we have 3 possibilities to remove the beta hydrogen. We want to remove the beta hydrogen that gives us the most substituted alkene. So we're going to have methanol, CH3OH. That's a covalent compound. We can't break it apart. That's a weak base. Lone pairs of the oxygen will grab that H. Bonding electrons will move to form a double bond. So what we will have is this. So here are your 2 alkene carbons. This carbon has 1, 1. This carbon 1 and 1. All right, that's a tetra-substituted alkene. So that's an E1 reaction. Questions on either one of these before we look at the next one? So let's take a look at this one. I want you to go through, see if you can go through with your groups, kind of work through the same way that we did, and determine what type of reaction will form, and then look at the mechanism. So look at the carbon that you have, look at what's over the arrow, how does everything work together? I gave you a secondary alpha carbon here. So you could have either one. When you have a secondary, then you're looking at what is above and below the arrow. So just looking at this first, then we can look at the mechanism. You have a secondary alpha carbon, and then you look at what is above and below the arrow. You have a strong base and an aprotic solvent. Strong base helps you to think about, okay, if it's strong, just like with a strong nucleophile, if it's strong, it has the strength to have the reaction happen all at once. So if it happens all at once, which reaction is it? E2. So E2, it's going to happen all at once. Now, if it's going to happen all at once, your mechanism really will be just in this picture. There's going to be lots of arrows. But we already labeled the alpha carbon. Find your beta hydrogens. Because E2, regioselectivity is based on, so this is a small base. So we're going to have the Zaitsev product, the more substituted. But figure out where are your beta hydrogens, which one should you pull off to give the more substituted alkene. This first beta carbon, how many hydrogens are on this beta carbon? 0. Right? This carbon already has 3 carbons connected. There are no beta hydrogens over here. So like when you look and you're like, well, this is going to be more substituted. Well, you can't form a double bond here because this carbon already has 3 methyl groups off of it. So there's no beta hydrogens over on this side. Our only option is one of these beta hydrogens. Doesn't matter which one you pick. Just remove one of those beta hydrogens. So, lone pair will attack, take the H+, bonding electrons will create that double bond, and then the leaving group will leave. Happens all at once. So in this case, there wasn't a where's our more versus less substituted alkene. We only had one option because of the lack of beta hydrogens over here. So the very last one, we have this cycloalkane, and then you see over the arrow, it's the T and then BU, that's potassium, right? Potassium's at the end here. That's potassium tert butoxide. Potassium tert butoxide is one of the more common bulky bases, right? K plus just allows this tert butoxide to come into solution. So this is a strong base, but this is a bulky base. So this is a strong, bulky base. It has that negative from the tert butoxide, but it's bulky. It's a very large base. That becomes important when it comes to type of product that's formed. So let's go through what we did before. This alpha carbon has what degree of substitution? Secondary. So here's a beta carbon. Here's a beta carbon. Secondary could be E1 or E2. So then it comes to our base. A strong base is more likely to happen all at once. The kinetics helps us to see that it's going to happen faster. If it happens all at once, what type of reaction is that? E2. So strong base, it will happen all at once. Now this bulky part means that the Hoffman product will form. Hoffman product is the least substituted alkene. Hoffman product means the least substituted alkene. So we have to find the beta hydrogen that is least hindered. Right? So we have beta carbon, that's where your beta hydrogens are. I have an option of here or here. You want the least hindered, so you want the ones that are on the outside of the molecule if possible. It's easier for that bulky base to grab. So what's going to happen in terms of the mechanism? Now because it's E2, it happens all at once. So you're going to have lone pairs attack one of these least hindered hydrogens. Right, these are our least hindered beta hydrogens. It has to be a beta hydrogen still. You can't pick a hydrogen that, is all the way over here, not even close to the leaving group. So lone pair attacks the hydrogen. Bonding electrons form a double bond. Leaving group leaves. Happens all at once. What that's going to give us is the least substituted, it's going to give us our least substituted alkene. So this is going to be the Hoffman product. It's going to happen all at once. If this were not a bulky base, if this were something just like hydroxide or like OCH3 minus, then it would have formed the more substituted. But bulky bases, you don't have a major and a minor product. It is just the least substituted alkene. So tomorrow we'll go through the quizzes just to help review. And then you also have the last page is the quiz review. So if you want to start looking at it now, you can. But you'll have time tomorrow as well.